So thank you all for coming. Thank you for inviting me. It's a pleasure to be here. I want to say what I said that I was proud of. I'm proud of Elizabeth Warren. So unfortunately, she dropped out, but fantastic woman candidate for President of the United States. So that's what I'm proud of. Thank you. So I wanted to talk to you today about some work that my team has been doing over really the last 10 years. I've listed a lot of my collaborators who are current collaborators both in my research team and also in our engineering team, Foundry 99, who we partner with to make all of this work possible. So private AI is our term for a kind of a new field, which is a mix of machine learning and cryptography. What do we mean by private AI? So AI is the term artificial intelligence that we're using these days to describe the kind of technological revolution that we're experiencing with our smartphones and the way that we interact with technology to help us through our daily lives and to solve problems from medical to financial to logistical. So a typical pattern, the way AI is used today, is that you want some kind of a recommendation, and there's some smart agents that are running as cloud services, such as Cortana or Siri or Alexa, and you ask them some question, or you ask for some kind of prediction or analysis. Could be anything from a classification of an image that you've seen, to asking for a restaurant recommendation, to something much more serious, such as medical diagnosis or prediction. So this type of AI is getting more and more integrated into our daily lives and our workflows, and in many cases, it can be very beneficial. The problem, though, is the trade-off. In order to get recommendations, you are inputting your private data. And a lot of times, that could be very obviously personal, or it could be things that you don't think about is that big of a deal at one point, but maybe at some later point, you could realize that it was personal information and it was used in a way that you did not want it to be used. So one example is location data. So where are you at every minute of every day? I'm pretty sure that most of you would not be very happy to think that somebody could have a catalog of where you had been every minute of every day sometime in the future, especially if some sensitive issue comes up and you didn't really realize that somebody was going to be able to pinpoint your entire location from one place to another. So that's the privacy problem that I'm highlighting here today, is that the more I talk to people even about the technical content of this talk, the more I realize that actually the fundamental message is the underlying issue of making people aware of the trade-offs of privacy when transforming ourselves into this AI society. So that is kind of my high-level message, is to just think about your own privacy and how we use our current systems today, and what kind of solution do we want to see, what kind of protections should we be thinking about having in place to protect our own privacy. So when you input your data to the, let's say, a cloud service, you're not thinking about what the future implications could be. So I just pulled some examples last year from news headlines, just to give you some examples of the type of breaches that you might not think about when inputting your private data. So one of them is a very interesting one. Strava is a fitness tracking company. So how many of you have a Fitbit or some kind of a fitness tracker on? Yeah, so I actually resisted getting one for a long time because of these privacy concerns. And I'll show you a demo at the end of something that we're doing to try to mitigate these concerns. But it came out in this article reported last year that locations and actual maps of US military bases around the world were disclosed because service people were going out with their fitness trackers on and running around doing their fitness workouts. And they actually not only gave away the locations of these military bases, but even like an entire map, like a detailed plan, just because they are running around the perimeter and things like that. So that's a kind of an example. And another example that ties to another demo I'm going to show you at the end is last year the city of Los Angeles was suing IBM over misuse, deceptive use of location data in a weather app. So often people, if you use your smartphone to see what the weather is, you'll be inputting your current location to find out what the weather is in your current location. And numerous other examples. Your location data is being collected from your phone on many, many different apps, I guarantee much more often than you think it is. So what I wanted to talk to you today was about a mathematical tool called homomorphic encryption. This is something that we can use to help protect privacy and security while still getting the value from artificial intelligence. So I wanted to just start by asking, so how many of you have heard about homomorphic encryption already? OK, good. Thank you. So a few people have, but it's good to know that most people have not. So first of all, the term, homomorphic encryption. I've been told by numerous executives, you need to change that term. This is not very pronounceable, not easy to spell, et cetera. Kind of something to impress people at cocktail parties. But so I'd like to just do a little exercise with you here, if you can bear with me. So I have two different descriptions of homomorphic encryption that I'd like to give you. And then at the end, I'm going to ask you to vote which one you liked better. This one involves Homer Simpson. So this is usually a popular choice. So Homer Simpson is a popular kind of cartoon character in the US. And when I've given this talk at leading cryptography conferences, and someone tweeted that I was talking about homomorphic encryption. So that's my new name for the technology. And so in this case, Homer Simpson is, in this cartoon, he's a jeweler. And he's looking a little puzzled, I think, because he's having to stick his hands into this box. He's using these gloves over here. The other side of the wall, he has to work on something that's in this box. So the idea is that if you have some gold, something very valuable to you, and you want to have some jewelry made, for example, but you're not sure whether you should trust the jeweler with your gold. You give them the chunk of gold, they make the jewelry, but maybe then they shave off some of the gold and keep it for themselves or whatever. So instead of just giving the gold to the jeweler, what you're going to do is you're going to put it into this locked box, this box that you're going to lock. So think of this transparent box over here. And you lock the box, and you keep the key. So put the key in your pocket. Do not give the key to the jeweler. And so now you give the box to the jeweler, but there's these gloves that the jeweler can use to work on it. So that's what Homer Simpson is doing over here. And when the jeweler is done, they are still able to work on the gold and get the jewelry made. And then when they are done, they're going to give you back the box. And since you have the key, you can open up the box and get out the jewelry and the rest of the gold. So that's the idea of what homomorphic encryption can allow you to do. You have some valuable data, which is analogous to the gold. And you want to get some prediction or some other kind of analysis, maybe data analytics, or build some kind of model from your data. But you don't want the jeweler or the cloud service to be able to take your data, use it for something else, or do anything that you did not intend with this data. So the idea of homomorphic encryption is that it can provide this mechanism for a locked box where the cloud service can still operate on your data, but without being able to decrypt it because they do not have the key. So that's the basic, in a nutshell, that's kind of my main message for this talk, is that we have this tool now, homomorphic encryption, and I'll explain a little bit more about it. But this explanation really tells you what is it good for. Why am I talking to you? It's because we can enable private cloud services, private AI with this tool. So here's my second explanation of homomorphic encryption. So this is a more mathematical one. So I'm a mathematician by background. And mathematicians love commutative diagrams. So this diagram tells you, instead of telling you what homomorphic encryption is good for, it tells you what property it has. So the property of homomorphic encryption is that if you take several pieces of data that you are represented here by the letters A and B, little a and little b, you can actually follow this arrow across the top of the diagram and compute on that data yourself. So for example, adding data together or multiplying it or actually performing any circuit, any set of AND and OR gates. So the top arrow is computing on the data yourself locally. And then what you can do is you could just encrypt the outcome of your computation. So that would be like encrypting A times B after you've already multiplied A and B together. So the other way to go around the diagram, starting from the top left corner, is to first encrypt your data. So you have several pieces of data locally, and you encrypt them and that individually. And then once they're encrypted, you have these ciphertexts representing the two different pieces of data. And you can operate on those ciphertexts, applying that same computation, that same circuit, whatever you wanted to do to get some kind of analytics or prediction. And the outcome that you get when you decrypt it should be the same thing. So that is the property of homomorphic encryption. And so while this defines, and the term homomorphic is a term that's very common in mathematics, which really means to preserve structure. So what it's really saying is that the encryption preserves the structure of the underlying data, and so that when you encrypt it, you still can operate on it, and it's meaningful rather than just being a bunch of garbage being combined together. So that's what the term homomorphic means. OK, so this explanation really focuses on the property that homomorphic encryption has, what defines it as a primitive. So I would like to ask for your indulgence here. So let's take a little vote. How many people liked the Homer, and there's no right answer here, OK? So how many people like the Homer-Simpson description better? Raise your hand. OK. How many people liked the more mathematical description better? Oh, wow. So the mathematical description is a clear winner here. And I have to tell you, I've done this vote in a lot of different audiences, and you can never predict which one's going to win. So always fun to see that. And also, OK, one more question. How many people voted twice? Yeah? Always a few. Good. So homomorphic encryption is a relatively new solution. So it's been a kind of an open problem in cryptography for 30 or 40 years. And the first kind of complete solution was suggested in 2009 by Craig Gentry at IBM. But this proposal was considered very impractical, and the underlying security and hard problems were not well understood. Very quickly, a lot of researchers were working on refining the proposal and coming up with alternate ideas. And a researcher in my team in 2011, Vinod Vaikachanathan, and his collaborator Zvika Brakersky came up with a new solution for homomorphic encryption based on a fairly well understood hard mathematical problem. And since he was in my team, we immediately started working together with other mathematicians in the team to make this solution practical and to start applying it to real problems. And so we came up with a lot of kind of practical innovations that made the technology much more efficient and usable, and started implementing it. And so just as another data point, 2016, we actually showed that you could evaluate deep neural net predictions on homomorphically encrypted data. So that was a pretty big advance in 5 years. to be able to do something that people considered to be very challenging and thought would not be possible to do to evaluate on encrypted data. And since then, there have been many research teams around the world improving those techniques to make crypto nets even more efficient and to evaluate deeper and deeper neural nets on encrypted data. So I don't have time to talk about everything I would like to talk about. So I have a couple of options, and it was suggested that I might take a little bit of a vote on this too. So I can talk a little bit about the mathematics of homomorphic encryption and what goes into it. Or I can focus a little bit more on the applications and what we're doing in this space to make it usable. So I'm going to take a guess on how this is going to go. I'm not going to tell you my guess. But who wants to hear more about the mathematics of homomorphic encryption? OK, and who would like to hear
15,
more?
15, roughly.
15, OK. And who would like to hear more about the applications? And I think the applications win. They win.
Definite winner.
So if we have more time, you can come back and ask me more about the mathematics at the end. So what we did starting in 2015, so this gets kind of right to the punch. If you're interested in this technology and you want to start using it, or you want to see what's being done, just don't forget what's called Microsoft SEAL. So SEAL is S-E-A-L, Simple Encrypted Arithmetic Library. And it was a project that we launched in 2015 to create, our whole goal was to create a robustly engineered, usable library for homomorphic encryption. And we were partly motivated by a lot of collaborations that we had had with people in other fields, such as machine learning, which is the basis for AI, but also in bioinformatics, genomics researchers, people that were really interested in preserving privacy and wanted to have a tool available that they could use to encrypt data. So this was quite different from the approach taken by other teams. Often research teams are hyper-focused on improving efficiency and performance. And what we decided to have as the core principle was usability and having a robustly engineered system. And so our SEAL was originally designed by a software engineer, and our research team has worked hard to improve the performance without breaking the software design and the usability, so that we now have what is probably the most well-engineered but also high-performing homomorphic encryption library worldwide. And the good news is it was publicly available since 2015 for anyone to use for non-commercial purposes. But in 2018, we open sourced the technology, which means that anyone can use it for commercial purposes as well. And it also means that people around the world are contributing back to the project and helping us to improve it. Now, there have been a number of other companies or entities who have even built software on top of SEAL now. So there's PySeal, which has been released. Dropout Labs has produced an encrypted version of TensorFlow, which is a machine learning package, which is built on top of SEAL, and numerous other projects going on around the world. So if you're interested, I really encourage you to go to sealcrypto.org. You can download the software, and you can read some of the documentation that we have there. So the next thing that I want to highlight is that this has been a very big community effort. Because when you think about it, I'm talking about this privacy problem, right? Protecting your privacy. And now I come along, you've never met me before, and I say, oh, well, I have this magic encryption thing that I'm going to use. And so here, why don't you use my encryption technology and encrypt your data? And so for most people around the world, how are you supposed to know what I'm doing? I say, oh, there's some complicated mathematics. I'm not going to tell you about it. And then I say, oh, and here's some software. So how are you supposed to trust this software? How are you supposed to trust this encryption scheme? How do you know, how strong it is, whether it's breakable, whether there's some backdoor in it? So this is a common issue for adoption of new cryptographic techniques. And luckily, as a community, we have more than 40 years of experience now of building trust in encryption technologies. And I can tell you a little bit about that process. And we refer to it as standardization. So what it means is that when there's a new proposal for cryptography, we have several stages of trying to get community experts around the world together to agree on things and actually standardize the technology. So in this case, what we did is we actually launched a consortium called homomorphicencryption.org to standardize homomorphic encryption. So we launched this community in 2017 with an open workshop at Microsoft Research where we got together in groups and wrote white papers about the status of the technology. And since then, we're coming up on our fifth worldwide standardization meeting, which will be held at the UN in Geneva in May. And the purpose of these meetings, there's usually somewhere between 75 and 100 people from around the world, and we have more than 200 on our mailing list. The purpose of these meetings is to get together to work on writing the documents and approving and refining the documents which specify the technology. So we have actually an approved homomorphic encryption standard since 2018. It was approved at our Toronto meeting here. And it's actually been written about, for example, in a report last year by the Royal Society in England. There's a number of libraries worldwide. I might not have the slide in here with the libraries around the world that have been developed by many people in this organization. For example, there's a leading library, SEAL from Microsoft. HELib was developed at IBM, and Palisade through DARPA funding. So these were all, roughly speaking, developed in the US. But the Heian library was developed in South Korea, researchers at Seoul National University. NFlib was developed in France, crypto experts. The TFAG software was developed in Switzerland, et cetera, et cetera. So there's many researchers around the world contributing to building this software. So hopefully that gives you both a flavor of what does it mean, what is the process to standardize new encryption, and also just a little bit of a taste of who's participating in this effort and that it really is a worldwide community. The next step is that various official standards organizations, such as a working group at the UN and a working group at ISO, are actually working on proposing and approving specific encryption standards for homomorphic encryption. So what I'd like to do is to kind of convince you that this homomorphic encryption has become relatively usable. So this is just a little bit of a graph over the last 10 years of how the performance overhead has come down. And let me warn you, this is a log scale. So what this means is that if you go back to 2009, the estimated overhead for using encryption was something like 10 to the power 13. So meaning if something took you 1 second on unencrypted data, it would take you 10 to the 13 seconds on encrypted data. So that's pretty bad. So that gave the technology a little bit of a bad name. Many people today still think that it's completely unusable and unrealistic. With our practical homomorphic encryption approaches that we introduced in 2011, where we changed the way that information was encoded and encrypted, and also the approach to designing kind of practical parameter setting and circuits for homomorphic encryption, we were able to bring down the overhead to about 10 to the 9. So that's still pretty bad, if it's a billion times worse than what it would have been without your encryption. And over the last 5 years, roughly, with improvements in both software engineering, algorithms for the underlying number theory, and improvements to the schemes, we've seen the overhead come down to roughly 4 orders of magnitude. So that means that something that might take you microseconds on unencrypted data would now take you milliseconds on encrypted data. And this is fairly reasonable for a lot of applications. The dotted line at the end here is supposed to indicate improvements that could potentially come from hardware implementations. So hardware acceleration using GPUs and FPGAs. It's already been investigated by our team and others in the research community. And in practice, we feel that it's going to probably give us another 2 orders of magnitude improvement. So the precise performance numbers change over time, but roughly speaking, there's a lot of computation that can be done on encrypted data in a matter of milliseconds, and often that is good enough for the applications. So let me talk a little bit about the types of applications that we can enable with this technology. Homomorphic encryption does not solve all privacy problems, but it can enable some type of solution. So one thing that it can enable you to do is to have private storage, cloud storage, and compute. So that could mean long-term storage of your personal data, such as even your emails or your photos, but that you could still have that storage be somewhat usable. So for example, searchable or having images being classified, that kind of thing. So it can also be used for just private AI prediction services. So one example, I didn't go into detail, but a demo that I used to show is predicting your likelihood to have a heart attack. So you put in a bunch of personal information onto your laptop locally, such as your age, your weight, your blood pressure, things that are a little bit personal. And that data gets encrypted, sent up to the cloud, and you use well-known models for predicting heart attack risk, and you get an encrypted prediction back, and you decrypt it. So that's an example of a kind of a private AI prediction service. And I showed a demo of that actually more than 5 years ago at in the newsroom in front of a live audience at the AAAS meeting. And the round trip, even at that time, took 0.2 seconds. So the data being sent up to the cloud, prediction done, and sent back. In 0.2 seconds, you don't even notice the delay. So that was intended to convince people that the technology was definitely usable for private prediction services, and it's only gotten better since then. Hosted private training, private set intersection, these are other examples of ways that we can enable a computation on sensitive data in the cloud when you outsource it. But the last one I'd like to mention is something that we're working hard on right now, is that we can even use homomorphic encryption to enable scenarios that are not really doable today, such as secure collaborative computation, where you might have 2 companies that have data sets they don't want to share with each other, but they want to get some kind of joint learning from combining their knowledge about their own customers, for example. And there's many different markets where this has been used. OK, so from finance to healthcare to manufacturing. So what I really want to make sure to save my last few minutes is to actually show you some demos of this technology in action. Hopefully that will be what you'll remember from this talk. So in the past, like I mentioned, a few of the demos I've done, such as heart attack risk prediction, and a lot of things related to healthcare and genomic privacy, which I worked on for a long time and I was very interested in. But today, I'm going to show you a few demos from this past year built by our team, which highlight a couple of applications that relate to some of those news stories that I mentioned in the beginning. So in particular, location privacy and medical health privacy. So this is an example of an app that we built called Azure Run. So Azure Run is actually supposed to be a private fitness app. So the idea is that just like I mentioned in the beginning, that I was reluctant myself to get a fitness app, a fitness tracker, because I was worried about the privacy issues. What our private fitness app does is it tracks your location as you, for example, go for a run. And that collects a lot of other data, such as there's an accelerometer and gyroscope, and it can even collect things like heart rate and stuff like that. So all that data is being collected locally on your device, and we're just showing it on the screen of your laptop here. This is a video of the demo, not a live demo. But this information, when it's collected from your device, is being uploaded to the cloud, but only in encrypted form. So on the right-hand side here, you're seeing what the cloud sees, which is a bunch of nonsense. It's just a bunch of encrypted values that don't have any meaning to it without the key. So then some computation is being done, for example, analyzing the intensity of your workout. So it's a fairly simple machine learning model that's being applied to the data to make a prediction on how intense was your workout. So that prediction is sent back to the phone, and then it was decrypted locally, and then you could see on your phone, you could see what the result was. Sorry, it advanced to the next screen, but you could see that it was predicted to be a kind of moderate intensity workout. So this is both a proof of concept that we can develop private apps today, things that were compromising your location privacy, could be built with homomorphic encryption with very little noticeable impact on performance, and could provide you the privacy, but still the value of the service, such as the fitness tracker. And in particular, what we did with Azure Run is that we also released this as a template for developers so that you can actually go and look at, this is not a service that you can buy. I'm not saying we have a private fitness tracker that you can buy. But it's a demo that developers can go and use to look at to see how to build encrypted apps. So that was the motivation behind Azure Run. So the next one is a chest X-ray analysis. So suppose you're at your doctor's office and they've taken your chest X-ray, and now they would like to have that analyzed by some kind of image analysis program. And they're going to upload it to the cloud and have the analysis done on your encrypted medical image. So not sharing the image itself with the cloud service, but sharing the encrypted image. And the analysis is done as to the likelihood of you having various diseases. It's sent back to the doctor, and it's decrypted by the doctor locally, who can then show you the results of the analysis. So this is an example of using this technology in the medical arena to preserve your health privacy. And finally, the last thing, this is really quick. If you don't look quickly, it'll go by without you even seeing. So you enter your location here, and it gives you the weather. So it already finished the demo. And the idea is that instead of just using your smartphone and putting in your location and finding out the weather, what this app did was to actually upload only an encrypted version of your location. And that was compared with the data that it had from all locations, and some encrypted value was sent back, which was decrypted for you, which was the weather that you saw in that area. So I'm glad I got a chance to share with you homomorphic encryption as a potential solution for some of our privacy problems in today's world, and to show you some demos of the technology in action. So thank you very much for your attention.
Kristin Lauter. Thank you so much. I'm sure there will be a few questions from the audience about homomorphic encryption. Yeah, there's already one. Or the possibilities to use it. Yeah, just 1 second so the rest of the audience can hear you as well. So who are you, where are you from, and what's your question?
I'm Abhijit Raghav, an undergrad student from India. So when we talk about private AI, does homomorphic encryption preserve the entire underlying structure and characteristics of the data, or is it still a trade-off between accuracy and privacy?
Oh, that's a great question.
Yeah, thanks.
So the answer is it can be either way. So every demo that I showed you today there was no trade-off in accuracy. We were doing exactly the same thing that you would have done on unencrypted data. However, in some applications, especially complicated things such as deep neural nets, there is this trade-off that you mentioned between accuracy and performance, really, even on unencrypted data. And often, the trade-off in accuracy is not such a big deal. Machine learning is a very inexact science, right? When you're making a prediction, you have some likelihood of being right. And so often, a tiny bit of inaccuracy, maybe in the third or fourth decimal point, something like that, is not only tolerable, but is not even necessarily worse than not having that inaccuracy. And so that is something that we now take advantage of in trying to improve performance. So many things you could just do with no loss of accuracy, but you could also take advantage of this trade-off, give up a little bit of accuracy in order to improve performance.
Yeah, thanks. Another question. Who are you, where are you from, and what would you like to know?
Yeah, my name is Daniel Peters. I'm from Berlin, so PTP. Do you hear me? Yeah. From the PTP Berlin, it's the German National Metrology Institute. So we're also working with homomorphic encryption, not with fully homomorphic encryption, more Polya, perhaps somewhat homomorphic encryption, because there's like a problem with the with putting everything into Boolean circuits. So my first question is actually, do you work on Turing machines here when you do the computations in your examples? And if, what about covered channels? Because you see through the runtime what is actually happening inside the program.
Yes, thank you.
Two questions.
Two questions, right. So first of all, I alluded to some of the practical innovations that we introduced early on. And I never use the term fully homomorphic encryption anymore. We loosely call it practical homomorphic encryption, where what we do is to focus on the computation that you actually want to do and model that with a circuit that has a certain depth and number of gates and things like that. And so when we set up the encryption parameters, we're already assuming some essentially finite amount of computation. We are not trying to enable a system that can do any arbitrary amount of computation in the future. Instead, we're trying to enable a system that can do the computation that we need now or that we predict that we need for that purpose. So very practically oriented, not theoretically a general solution. So then, second question was?
If you have a general solution, but you said you don't have it. I mean, if you would run Turing machines, actually, through seeing the runtime, if there's a condition and you break through it, normally if you have a Boolean circuit, you have to do all the computations. But in a Turing machine, somebody could see, okay, in this step, the program took this direction, so I know exactly what the value was.
Yeah, so let me give you a little bit of a more general answer. So one thing that I think the core skill that we as cryptographers develop over time is modeling trust. So the most important question whenever we're talking to customers or consumers about privacy problems is, what problem are you trying to solve? Who are you trying to protect against? And so I didn't talk a lot about that here, but I was kind of implying that mostly we're trying to protect the data, so your personal data, such as your location. But you could also ask, well, if somebody's developed a model, or do you want to protect that model? Is that model supposed to be private as it's being applied to data to give predictions? Or you could ask for even more stringent privacy, like do you want it to be private, even who you're interacting with or how much data you're uploading or things like that. So a number of those things are not being protected by homomorphic encryption, including the models are notoriously hard to protect. So as you evaluate a circuit, be it a Turing machine or whatever other circuit on the data, it is very likely true that you will leak data about the model in several ways. One could be just side channel from computation time, but another way is actually nothing to do with encryption. Just when you give repeated predictions using a given model, you can end up leaking information about that model, even if you didn't encrypt anything, even in the unencrypted case. So thanks for pointing that out. But what you're really highlighting is that we're not necessarily protecting everything with homomorphic encryption. This talk was primarily focused on explaining how we could protect your private data. Mm-hmm.
One more question?
Yeah.
Just one more.
Okay, and I'll come to you. Yeah.
So then because we also, I said we're working for PTP, we are working with smart meters, and this is actually, yeah, thank you. So we're adding data together. This is why we're just using Polya, for example, to say, okay, we have one meter that has an output for electricity, the other one has as well one meter, and it comes together at one station, just an add of two numbers. Now the second step for our project is, for example, that the provider cannot see the individual data, not the number of the individual meter, but when adding all together, there will be the clear text results, so functional encryption. How do you see functional encryption? Does it work with the library, with the C library, and where are we there? Where we actually just want to hide the input, but the output should be visible for the provider actually afterwards to bill the user, but without knowing the individual results, but the overall result. How far are we with functional encryption is actually the question.
Yeah, so we haven't focused on enabling functional encryption in the CL library, but it's a good point that it is something that we could consider. However, a lot of what you might want to enable could be done simply by the process of having a service that just decrypts particular answers, you know. So in some sense, you could say that we're locking the data down more, like kind of the maximum amount, and then we can still enable the functionality by just having a decryption at the end for whomever we want to enable to decrypt.
Yeah, okay. Who are you? Where are you from?
Tim Jacek. I work for 1QBit Information Technologies in Vancouver. Could you elaborate a little bit on the security of this homomorphic encryption? Because it seems like if you know only a few images, you could get information about that mapping in your commutative diagram. How does it compare to state of the art?
Yes, good question. So there's two key points to make about security, and then there's a lot more complicated things we could discuss. But number one key point is that this is randomized encryption. So every time you encrypt something, it looks different. So you encrypt 0 twice, it looks different. And you're not supposed to be able to tell whether it's a 0 or a 1. So that's a very key point, because if you use deterministic encryption, then you have all kinds of avenues to attack where you can repeatedly encrypt things and check whether it matches and things like that. So you can do traffic analysis. So it is randomized encryption, which is very good from the point of view of security. But it has another kind of, I would say, a flaw, which is that we're trying to enable computation. So that means that when you add two ciphertexts together, it's supposed to have meaning, right? So for example, if it's a public key encryption system, that means that anybody can use the public key and encrypt legitimate values. And then by the functionality of the system, you're supposed to be able to add together or multiply together encrypted values and get something meaningful. So that means that somebody who wants to tamper with things in a public key setting can actually encrypt values, have legitimate encryptions, combine them if they kind of intercept the communication, and inject. One option is always just to kill the communication channel, kind of denial of service attack. Another attack is to just inject garbage and make your communication channel useless. But this is a third thing that's now possible, which is that a determined attacker in a public key system can encrypt things and change what was supposed to be your legitimate values to screw up your system. So in the secret key setting, they would not be able to inject anything meaningful, because they don't have the key to encrypt anything either. And that means they're reduced to simply destroying your communication channel and injecting garbage. So those are the two main points I would like to make about security.
Thanks.
Any other questions? Yeah, final one. Who are you? Where are you from? What would you like to know?
Sure. Hi, my name is Ankit. I'm a high school senior. I'm from the greater Washington, D.C. area. I'm currently interning at a cybersecurity company. That's the paper that we're presenting today. But I've also done a lot of work in medical diagnostics, so like stroke diagnostics, heart murmur diagnostics throughout, I guess, my high school career. One question I had was related to your chest X-ray analysis. So this is something that I've seen like a lot of researchers across plenty of different universities have been like applying convolutional neural networks and a bunch of different machine learning tactics. So you mentioned how in terms of like the creating like a more secure form of like chest X-ray analysis, you would have the analysis done on the encrypted medical image. So does this also mean that you would have to encrypt the data set that you're working with? And if so, how computationally expensive is that? And what types of approaches have you sort of like undergone in order to try to maximize accuracy?
Oh, that's a great question. Thank you. And I consider medical applications to be a really important and interesting area to try to protect privacy, but also very challenging. So a high-level comment is that a very high percentage of all medical data that's stored in the cloud is images, just because images are so large. So it is a big target space. And we did a pilot project with Median Technologies, a startup company in France, that has some approaches to basically abstracting kind of metadata from images to make them smaller. And so one pilot project that we did with them showed performing analysis, but on this metadata, which was smaller than the images themselves, so easier to encrypt, taking less storage, less compute time, everything. So that's one kind of approach that we've taken in some cases where you're not encrypting, pixel by pixel the entire image. And we've only done a couple of pilot projects in this area, so I really think that there's a lot more work to be done, but that should just give you a flavor of one of the kinds of things that we've tried in practice.
Thank you so much. Kristin Lauter.
Thank you.